Okay, so let's take a look at the plan for this week. We'll cover the operation for the DC-DC converters. So last week we covered AC to DC, which are the rectifiers. And after the output of the rectifier, you want to connect a DC-DC regulator or DC-DC converters to that output and receive that signal as the input for the DC-DC converter and stabilize everything to the desired voltage, like 5 volts, 3.3 volts, so on and so forth. We're just going to qualitatively, not quantitatively, do analysis for all these, the two different types of DC-DC converters. And we'll cover sensors and actuators for 2 to 3 lectures. We'll see how that goes. Hopefully we can get everything done as soon as possible. And there will be 3 or 4 homework problems for you guys. The first one is a pretty simple calculation for the strain gauge. It's called Wheatstone bridge. It's a sensor for calculating or measuring the variations of the resistance. Typically, we use that for the strain gauge. The typical application for strain gauge is, the scale in bathroom, okay, something like that. And it definitely has many more applications, not only that. So for example, currently for my equine project, the lameness detection project, I'm not only using an accelerometer to detect the speed of the hoof, but actually in phase 2, the customer probably will be interested in looking at the strength of the hoof. So whenever the strike is hitting, so the hoof is hitting the ground, we can measure the strength of the hoof over the legs of the horse. So you do need something like a strain gauge to measure that strength. And you'll need a Wheatstone bridge as well as a sensor to convert the resistance change of the strain gauge to a voltage change. So you can use your ADC analog to digital converters to detect that change. And the problem from 2 to 4, they are some fundamental Arduino projects. The second one is not related to the balanced car project. But starting from the third one, it's actually preparing you for the balanced car project. Okay. Especially the fourth one. So this is different from the microcontroller class. I already gave you the code on my website. So for these 2 ones, I didn't give you any example from my end, but actually there are a couple of other examples I already uploaded to my website. They can be a good reference. You can take a look at the sketch over there. So we're going to use a joystick to move the rotation direction, and speed of the stepper motors. And the stepper motors are being used for your balanced car in the future. Okay, so you are actually trying to make a communication between your joystick to the stepper motor. So the stepper motor is not on the car yet. Probably just one motor here. You're just looking at it and use the joystick to move it around, so you can start it and change the speed. So we'll get into that probably in the end of this week, hopefully, if we can get everything done. All right. In your senior sum, meetings or teams, so what I heard from the other people, like so the different teams, hey, I need a CE student here to help my project or something like that. So they can already tell you guys are on demand, in demand, right? It's the same as, after graduate, if you go to the market, they do need people to be able to work on all these things, programming, digital controllers. Do you still remember how the inductors work? So let's start our DC to DC converters. I started recording. Okay. What's the major equation for this inductor? And here's V, definitely, because that you have a voltage source, DC source, you cannot change it. So V here, frozen. V here. So I is changing. Is V changing? No. After turn on the power supply, it's going to be V applied to the inductor. So it's like something is trying to resist the current being pumped into the inductor, right? Like a teenager, you tell the teenager to do something, he just doesn't like you, don't want to listen to you. You apply a voltage like this, okay? But afterwards, the current will flow into the inductor, and finally the conductor performs like a wire, eventually. So uh, the equation for the inductor's operation is V equals to L dit dt. Is that right? Okay, dt. And which means I equals to what? So there are only two very fundamental equations you need to remember. One for inductor, one for capacitor. These are the two main nonlinear components we're using in any circuits, right? So the inductor, just remember L di dt. V equals to L di dt. And for capacitors, what is that? So it's going to be, for capacitors, it is I equals to C dV dt. Right? That's for capacitors. Still remember that? It's been a while, right? No, you forgot? Okay. But for now, this is a given. That's the behavior of the inductor. And IT equals to 1 over L. Just move L to the left side and move V to the right side. And no, you don't. You move T to here as well. So L to here, so 1 over L. And move T to here and integrate on both sides. So we get IT equals to L, 1 over L. And what? Yeah. Wait. I equals to, yeah. Is that right? So that means, because V is constant, right? So I is changing. Why I is changing? So V is constant, but I is a function of T. Is V changing? No, V is a constant. So I is changing. Yi is changing because they're integrating T over time. So it looks like this. T, IT, then what? Hmm? Is that a line or a nonlinear line or curve? So for example, okay, just for example, I'm going to integrate this guy from 0 to t. And v is a constant. So what's the result? Right? And v over L is a constant. So it's going to be v over L times t. So it's going to be a line. And that's how I changes. What's the slope? Hmm? V over L. Is that clear? That's pretty much everything about inductors. That's it. Not really difficult. But I have to remember this first. Is that clear? Okay. So given that, I got a few cases for you to look at. Case one, if I have a voltage source here, which is V1, and here's grounded, and V1 is like this, V2 is a little bit larger than V1, so two DC voltages. So I want you to plot I, L for me, which means at some point, I'm gonna change the switch to here, just move it to here. But at the very beginning, I have a constant voltage V1 to charge up the inductor. So when you are using a DC voltage source to charge up a inductor, what's happening? Yeah, the current will linearly increase until a very large level because you don't have a resistor to limit the current. So it's actually literally infinity. It's going to go to infinity because the inductor eventually will perform like a wire. Okay, that's why it's going to keep going until something's burned. So it will start. I'll start from here. For example, it's been on for a while. Okay, like this. What about the next phase? Yeah. Hmm. Actually, steeper, right? Steeper than this. And case two. V1 and V2 is negative. The first one, pretty simple, right? Is that correct? But V2 is negative, so what's going to happen? So whenever the switch is being moved to here, V2 has a different polarity. So what's going to happen here for this phase? Yeah, so when you are integrating, just look at this equation. So when you're integrating a positive number, you get a positive value. When you are integrating a negative number, you are subtracting from the original level. So it's going down. Going down from where? From here? From here. From the top. The reason is you have an initial condition here already. You already stored all the charges in there. So it has to decrease from there. Steeper or not, or slower? Look at the absolute value. It's not going down as steep as this one going up. Okay. Case 3. Do I still have space? No. V1. Apparently V2 has nothing. So pretty simple. Here is this. What about here? Still look at this equation. It integrates because you have an initial condition, which is in the past, it's been integrating to a level. But after a time point, it stops integrating anything because the constant here is 0. So integrating a 0 in any period will be 0. So what's going to happen? Flat, ideally, right? Okay, this is helping you to understand inductors. Recall your memory if you have some. No. All right. Now, let's look at the buck converter circuit. I'll start a new page. So the buck converter is stepping down or stepping up? Stepping down. So if I only introduce the buck converter to you guys, it might be fine. You probably can remember it. But if I introduce the boost converter later, they are pretty similar and using the same component but in different orders. It's really easy to get confused. That lets you know how to differentiate. If you understand how that works, it's pretty easy to remember, actually, not that hard. So if you ground here, and that's a VL, that's a load resistor. So that's the filter, can smooth out the output like a bucket reservoir of charges. So the way this guy works is it is able to turn on, turn off this switch really quickly. So definitely it won't be a mechanical switch and somebody is sitting there to turn it on, turn it off, right? So you can use a CMOS transistor in the future and use a microcontroller to turn on, turn off the gate in order to perform like a switch, but being operated quickly in kilohertz level. And so when this guy is on, let's take a look at what's happening here. When it is on, there's nothing happening here for the diode because it's inverse voltage, so it's not being turned on. The capacitor, after you have turned on this one for a while, The capacitor is not conducting DC current. So this is also a disconnect circuit. So literally, it is just your power supply and the load. So it's flowing like this. After a while, the inductor will perform like a wire. That's how that works. Even though it's performing like a wire, but also, since it has current flow through the inductor, so the inductor stores energy inside. It like a wire, but it's not a wire. All right, so it stores energy. And once you open this switch, so the power supply is not being used. Actually, it's not pumping any current into the circuit anymore. So but before that, you have here is plus, here is minus. Before it's getting stabilized. I mean, after a while, it's a wire, so there's no potential drop. But before that, you reach that level, you reach that point. Here is slightly larger than here, if there's any resistance inside. Okay. After you open this switch, you don't have this part anymore, and this guy works like a battery. It's going to discharge itself and pump the current to the circuit, and it's going to work like this. Okay. So when this one is open, you have this. And the current flow in this way. And this works like a battery, like this. So if you turn on, turn off the switch like this, and you got your IL. So this is V in. So what IL looks like during these cycles. So here, like that. This is VO. This is VO. That's V in. That's here's no V in. So IL equals to what? Remember that I equals to this, right? So actually, if you move this one to here, you're getting delta I over delta T, which is a slope, equals to V over L. So for when the switch is on, you're having this. What is VL? So what is VL here? So here's V in, here's VO. So VL equals to V in minus VO. Right? So for this period, remember that's a DC V in. Remember all these cases I just drew here. Okay, when you have a DC voltage, you are getting a linear line. Yeah, so it's gonna increase. And what's the delta I here? you get a delta I, right? Delta IL equals to what? Equals to the voltage across the inductor over L times T. So delta I, here's delta I equals to the V across the inductor, VL, over L times delta T. So this equals to V in minus VO over what? L times what? T on. That's T on. Is this correct? In your humble opinion, is this right? And then whenever it's being discharged, like in this cycle, it will go down to here, and let's try to calculate what's the delta I here. So when you have this circuit, what's the voltage across the inductor? Assume this is ideal. No V in anymore, because right now the switch is closed, is open. We got a V in here, but actually this is like this, right? Disconnected. This is not working. So let's be clear. Let's jump out from the calculation and let's just look at these two modes. So the buck converter is pretty simple. You got a circuit like this, and you have a switch, and there are only two states, on and off. Just very simple. You turn it on, you charge up the inductor, okay, you convert the electrical current into the magnetic field into the inductor, you store the energy into the inductor, and whenever you open the switch, it allows the inductor to discharge itself, to convert the magnetic field into electrical current again, and then to power up your circuit. Okay, that's it. Charge up, discharge, charge up, discharge. There will be an up and down for the current because it's not ideal, and it's losing the energy. It's converting the magnetic field into electrical current. So it's losing energy. So that's why it's charging up, lose, charging up, lose. Okay. If you have a longer on time, so which means not a square wave, not 50% duty cycle. It's going to charge for a longer time, and so it's going to go up higher, right? And go down faster, and go up higher and go down faster, like that. If you have a shorter on time, so it's not able to go too high. So what is actually controlling the final voltage as the output of the buck converter? The speed switch, or you can say the duty cycle of the switch. So it's literally a PWM wave. Is that clear? So normally, for the inductors, value, inductance, and the capacitance, they are not critical. If you use TIs, I forgot the name of the website, like WebBench or something. So it's in CE432 class on the website. In your first tutorial, the PCB tutorial. So you are trying to use their website to calculate the values for these two ones. It doesn't have to be exactly that value, okay? Keep in mind. If you use 46 microhenry or 33 microhenry, it's not affecting too much. It's not really critical. So what really matters is actually the duty cycle. So the buck converter or the boost converter I'm going to introduce pretty soon, they are both switch mode DC regulators. Remember this word, switch mode. So during the interview, you are not embarrassing yourself if they ask, what is a switch mode power supply? Okay. So there are switch mode power supplies, which has normally has higher efficiencies. You can see switch mode power supplies in a lot of high current applications because they have inductors. But doesn't like the AMS 1117. So that's not a switch mode DC regulator. So it's integrated circuit based. So finally, it has a reference voltage and stabilize everything to a certain voltage. We're not designing a circuit like that, but the power will be lower for the other ones. But switch mode power supply has been super popular because it has definitely higher power. Okay, so that's the way how this operate. And I'm not done yet. So we are here. So I know we have been trying to look at this, but intuitively, I hope you can understand how that works. Okay? It's just like if you have a longer on time, because we have the inductor in there, so actually it can go up longer time, so it can reach a higher level. That's it. If you shorter your on time, when it's going up, it just stop going up at a certain point. That's no, it's so that's another mode. It's called not continuous operation mode. But for this continuous mode, it's always able to go down to the so at the very beginning, right? So it's going up to a certain value, but however, after a certain period of time, it is always able to go down to that initial value. So go up even though you change the time, but there will be a limitation. You cannot make it too long for the off time. Even though you shorter your on time, it go up, but it's still able to discharge to the starting point of your of the on period. You know what I mean? So it is able to come back. So if you have this, because it's not starting from zero, it always have some residue energy stored in a inductor. So do this, it will come back to here. But you couldn't make this too narrow. If you make this too narrow, probably it won't reach that. So there will be some limitations. How that works, I didn't get into details about this actually. If you so what I have seen is if you make this too narrow, it is just not able to come back anymore. So it enters another mode. It's a discontinuous mode. I couldn't explain this intuitively, but I will think about this later. See how we can make this more intuitive. But based on the ones we are working with, we are always working with all these continuous ones. So assume that it is always able to come back to this baseline. So you are finally getting, if it is charged to here and come back to here, go to here, go to here, and if you filter out the output, if you can see that the average voltage here will be somewhere here, and the average here will be somewhere here after use a low pass filter, right? So the ripples will be reduced after all. Won't be pure DC, but will be a lot better. That's how you can stabilize the voltage to a different DC levels. Okay. So this one equals to this, but this is on during the on period. What about this? Here, what's the voltage across the inductor? Here, 0. Yeah, if we just use a positive value, we just look at the delta t as the absolute value. So it will be, so the delta I here will be VO over what? So VO minus 0, right? So it's actually VO. V over L times T off. Because we assume this one will come back to the baseline. So this equals to this, right? Which is this. Move this to the right. Cancel. So VO over V in equals to T on over T on plus T off. And what is this? Yeah, it's pretty simple to calculate actually. If you want to get a V out, specific V out, only thing you need to consider is actually the duty cycle of the pulses of the switch. Okay. And I think next we are going to look at the boost converter. When the switch is closed, what's going to happen? When the switch is closed, yeah. So here this line is going to short all the other things after this line. So I'm getting this. And if you open that, We're getting this. How this can boost your VL, how that works. So think about this for a second. Why? So after close the switch, this allows the voltage source to charge up the inductor. So it stores a lot of magnetic field that's ready for pumping the current out from the inductor later on. And now I got this, and then start charging up the circuit, the load, like this. But however, whenever you close the switch again, nothing is coming back. All the charges will be stored in the capacitor. But the diode will block anything come back. So you can imagine every time it's going to boost the voltage level here a little bit. So it's going to stepping up until a certain point. If you do a simulation, you will see that it's actually giving a little. So every time you open the switch, you'll see a little surge of voltage. So here it will be a little higher than here. So we'll dump a little bit more charges to the capacitor. And it's going to be stored in the capacitor without going back because of the diode. That's how you can boost the voltage to the output. So the way to remember if you look at the different circuit schematics, and you are trying to tell if this is a buck converter or boost converter, what's the key point here? Yeah, the location of these three parts, right? So the key point is the inductor. And if you remember this part, you need an inductor to give a surge to the diode. That's how you can boost the voltage. That's a key thing to remember the structure of the boost converter. So you always need an inductor in the front of the diode. But for the buck converter, what you need is after you open the switch, you need your inductor to discharge to everywhere, including the diode over here. Hopefully that will be a little bit more helpful. Then the waveforms. Oh, that's actually be in. So what's happening here? Do you have a different delta I every time? Let's think about this. Do you have a different delta I every time after everything is stabilized? Let's look at delta I like this. And here is for this one, VL, so delta I equals to V in over L times T on. I mean, after everything is stabilized. At the very beginning, it's not like this. So it takes time to rise to this point. You know what I mean? So at the very beginning, it's like this, and eventually stabilized to a certain voltage. Okay. So the delta I will be the same because it's stabilized at a certain DC voltage. The delta I here equals to, what is it? Because VO is higher than V in, this is a boost converter. So it will be, if we only look at the absolute value, it will be VO minus V in over L times T off. And if these two guys are equal, we are getting this. They are equal because this is stabilized, so it's not going up anymore. This times this equals to V over VO minus V in over L times T off. And what's next? So V in over L times T on equals to VO over L times T off minus V in over L times T off. And move this one to here. We're getting V in over L T on plus T off equals to V over L T off. So cancelled. V over V in. V over V in equals to T on plus T off over T off, which is what? So that's T, that's a period. That's a time for the off time. And this is larger than 1. That's why VO is larger than V in. And this is actually 1 over the duty cycle of the off time. Is that right? Because T off over T will be D off, the duty cycle of off. So this is literally 1 over D off. Because D off is always smaller than 1, so 1 over this guy will be larger than 1. And that's how the signal gets boosted. So you can estimate the V out using this when you are looking at a boost converter. And that should be the only parameter to calculate for the output voltage of the boost converter. Since we don't have L, we don't have C, we don't have anything else. The only thing here is the duty cycle. Pretty similar to the buck converter. All right, so that's DC-DC. And there's another category. The solar panels is also DC to DC. And sometimes you need to convert the solar panels DC to AC. Do you know that? For the houses, right? So you have solar panels on the roof, and all the appliances at home are AC. So you need to convert the DC voltage from the solar panel to AC. There are actually 2 categories. You can directly use the solar panel to power up your robot sometimes. But definitely, so what are solar panels? Do you know? Have you ever heard about that? What's the mechanism of the operation of solar panels? Yeah, photoelectric effect. 2 layers. It converts photons into photocurrents. So because you have p-n junctions, and which can convert the photons into for the current, right? And accumulate the charges to the two terminals so you have a voltage at the two terminal part of the solar panel. So it's DC, it's not AC, because it's not coming from the generator turbine, right? So it's a DC voltage. If you are using a portable solar panel, you can buy on Amazon. Actually, there are so many different solar panel kits you can buy, and to power up a little car or a little robot or something. But do you need to convert that voltage to AC and AC to DC? Nope. Okay. So what you actually do is, for example, we do DC to DC. Okay. So you do this solar panel. There will be two terminals for the solar panel. And you need a charger. So there are, I got a name here. So that's called TP. For example, that's one of the available off-the-shelf chargers. TP4056 module you can buy. And this is a battery charger. And then battery, chargeable battery, like this. And then what? Before your Arduino. Yeah. That's how you deal with the DC to DC solar panels. But for the solar panels being installed on the roof of your house, you need to convert it into AC. So here's how to do it. That's a solar panel. And you have this. Couldn't even remember the circuit. That's a load. Your microwave, fridge, okay? Anything at home. And you keep these two off and you keep these two on. What will happen? Solar panel provides DC, right? Then what's going to happen? These two on, so current flowing that way. Okay. In the next phase, you open these two switches, but turn these two switches on, so it will flow in that direction instead. So actually, the load is experiencing this, right? Is that correct? Alternating voltage. Right? But still not AC. It's square wave. It's not sine wave. How? PWM. So you don't keep them on off at the same time period. You keep one longer, one shorter. So you are eventually getting something like this, for example. Then what's next? You haven't done that before, but this is a fundamental principle of a lot of circuits. Not integrator is fine, but not literally. You can just use a low pass filter. You know what I mean? So for here, you only have a pretty short on time. So that's why, because you are not allowing the capacitor to be fully charged and discharged. So it's going up, but cannot go down too much, and then go up. And here, it has more time to go down, but however, it got longer time to go up, like this. I'll draw it like that. And you smooth out this wave, you are getting a sine wave. That's how that works. The same thing for the other cycle. Okay? But never mind, it's just something to let you know. And the name of this guy is called inverter. You see the barrier between the engineers. These are power electronics engineers. And if you grab someone from IC design industry and tell them inverters is this, right? They're using the same name, but actually totally different inverters. Okay, so that's everything we want to cover today. On Wednesday, we'll cover a little bit about DAC. You have been using ADC, but we'll cover a little bit about DAC. And then we'll start our sensors and actuators lectures. Okay.